And what's the antiderivative of secant u tangent u? Secant u. So this would be negative secant u. Did y'all remember the plus c? Now plug back in your u. So negative secant, and u we said was cotangent 3x. So secant of cotangent 3x. Good morning, Coach Kersey. How are you? Good. Does that make sense? Yes. So would you say 6 or 16? All right, well, I'll do 6 first. 40x cubed. Yeah. That's okay.
When you go from how do you to it going away in the final? What happens?
Well, okay, so anytime you take the integral, right? If I do the integral of even just x dx, in order to do the integral, I've got to have that dx in there. That's part of the integral. So to evaluate what's the antiderivative, I've got to have this, and it's got to be in terms of the same variable that's in there. If I just said this, that doesn't have an integral. It's got to have the dx. So the du allows me to take the integral there. So this would be, of course, 1/2 x squared plus c. Correct, correct. So you've got to have that du in its entirety. Does that make sense? So you've got to have everything that's in your du, you've got to have in that integral before you can evaluate it. And then you just sub it out. So this and this, we didn't have the -1, but we put it in there. All together makes up that du. Well, because the 3 inside was positive, but on the du it was negative. Does that make sense? Somewhat. Let's look at this one. Okay. 5x to the 4th plus 3 to the 4th. I'm thinking 5x to the 4th plus 3 is my u. What did y'all use? So for those that are having trouble coming up with the u, tell me your thought process when you chose the u.
That's what I like that. I like that.
I always look at what's a function of something else. That's how I usually look at it. Whatever is like the innermost function is usually going to be your u. Not always, though. There's different ways of looking at it. It's hard. I think I told you yesterday, that's the hardest part for me, is determining what's going to be your u. Once you figure it out, though, what's your du here? 20x cubed dx, right? Okay. Let's look at. You're going to put the 2 outside. You'd have a 2 outside because you'd need a 1/2 inside to cut that 40 in half. You have to counter it on the outside. Right. So here, and let me just write it out this way. So I got 40x cubed over u to the 4th dx. Everybody okay there? So now when I compare this to what I have for my du, how am I going to make it look like that? Well, half it inside, but to move it to the outside, right? So here I would need a 1/2, but I need to counter that on the outside, and that's where I do my 2. Yeah. So you'd use a 1/2 inside, but you do the opposite on the outside to counter it, so that it doesn't affect it. Does that make sense? Well, if you were to multiply 40 by 1/2, you end up with, so now I've got 2 times 20x cubed over u to the 4th dx. Well, now this looks exactly like that. Correct. It's kind of like if I was in this equation and I had 40x cubed equals, I don't know, 17, and I wanted to make this 20, but I can't change. Instead of multiplying both sides by a half, what I could do is just multiply by a half, and also on the outside multiply by 2, and I haven't changed any values. That's essentially what you're doing, is you're working, because you don't have the other side of the equal sign. You're working on just that one side.
So then you would make, so in order operations, you have to have 20.
Right.
What you're doing.
Right. You can do that. So that's what we were talking about that other way yesterday. Yeah, you can do that. So she came to this, and she said, well, I could multiply both sides by 2. 2 du. Well, so then instead of doing a half and 2 here, she just said, well, all of this equals 2 du. So where we got 2 integral, I'm going to change this to -4 du. She got u to the -4 2 du, and then she pulled the 2 out. Either way you want to do that's fine. She did the same thing. It just depends on where you solve it. Do you solve it in the beginning? Do you solve it in the end? In the very beginning, I agree. I think that's probably easier too. Yes, so what she's saying is in the beginning, when she first started, she changed that problem to 40x cubed u to the -4 dx, and it was easier for her to see. She changed that to a negative. You probably did it there, didn't you? As your u, it won't work for you. Because you always want to choose your highest power for your u. Because remember, you got to go back and derive that u. So your highest power is always where you start for u. Yeah. I take it y'all have it from there. Y'all didn't. I mean, you. Go ahead. No, you don't have to. Then, of course, that's 1/3, -1/3 u to the -3rd. Is that what y'all got? Because it's just the u with one exponent. So add 1 and then divide by that here, right? And then plug the u back in, that's right. What was our u? 5x to the 4th plus 3. -2/3, 5x to the 4th plus 3, -3. If you put that on the bottom with the 3, that's fine too. Does that make sense? What other one did you say? 16. Ooh. This one looks a little harder. What's the challenge here? You don't have one that's just one power less. 9 plus 16 is to the 10. You gotta have what? I don't know that you have to have 2. Won't you what? Which, as soon as I saw this one, I'm thinking this is an inverse trig function because of the bottom, right? What'd you do? You have to what? Well, I'm thinking if we think about this being an inverse trig function, no, but if I want it to look like that, if I want it to be 1 over 1 plus u squared, did she just get it? All right, Lizzie, tell us what you did. You can't just take the square root of everything like it is right now. What? Well, as I look at this, I know that something's going on. I'm going to have this x in the bottom. The exponent's bigger in the bottom already. And so that's leaving me. And I've got a value plus something with an x squared on it. I mean, an x to a power on it. So something plus a variable. So look at your derivative sheet and look at the ones there. Oh, but the square, you can't do it. You can't do that. I need to get that down. I'm gonna have to look at this one. I'm gonna have to sit down with my pencil and paper. Let's do another one, and that's all you had questions for. Okay. All right. Let's move on. Yeah, turn in, but I'll sit down and work that one out and figure it out for you. All right, ready, Freddies? Okay, switch gears. Once I get through this, I'll give you your stuff, and then I'll let you work on your test corrections a little bit more. If you turn in your homework without that one in there, it's fine. Indefinite. This is more Usub, but we're going to do it in definite integrals instead of indefinite. Oh, more Usub. I feel like that. Can y'all see that writing? No. So what's the definite ones are the ones with the bounds on them. In, yeah, not in, I'm sorry. Yeah. Usub using definite integrals instead of indefinite integrals. Yeah, right, using. All right, y'all ready? Christmas ready? They picked up breakfast from the cafeteria back there.
Oh my God. Yeah.
Look, you come in here and you get fed. Do what now? Yeah. There you go. All right. We're going to go through the exact same steps here that we went through before. The only difference is now we're going to use that fundamental theorem as we evaluate, right? So if I do Usub, yeah. But, well, it's a little bit different because my bounds here are in terms of x instead of terms of u. So we're going to have to take that into account. And so there's two basic ways to go about this, and I'll show you both of them. But here, if I were to evaluate this, first of all, how do you know this is a Usub problem? You've got the x squared and the x. I told you it was Usub. But you don't know the antiderivative of this right off the top of your head, right? It doesn't look like any other type. It almost looks like one of the inverse trig, but there's an x up top too. So what might you let u be? Look at y'all. An inverse trig function here? No, because the x up top, there's well, remember, if you separate, there's not a property that lets you separate the integrals by multiplication. That's why. So I couldn't do the integral of x times the integral of 1 over x squared minus 4. That's why. All right, what's du? 2x dx, right? Do you have a 2x dx? No, but you can multiply by 2. All right, so remember, if you want to solve this one, if you want to multiply both sides by a half and say, well, 1/2 du is equal to x dx, or if you want to do the little counter process, I don't do it that way either, but whichever way you'd rather do it is fine. So I know that I need a 2 here. I'm going to put a 1/2 here. That's my thought process there. All right, so I have 1/2. Yes. What? My du was 2x dx, and I just have x. Yes. From 0 to 1, and I have u to the negative 1 du now. Agreed? Disagreed? Whatever you do to the inside, you have to counter it on the outside. It has to be the opposite. All right, I'm going to put a note here. Watch the bounds. Now, I can go through here. I can find the antiderivative and then sub in my u and then put the bounds in. Or my preferred method, I can change the bounds now. Right now these are in terms of x, right? Why don't I just change them in terms of u, and then I won't have to do as much work. I'll show you both ways. Well, I know right. You just plug it in to what your u is. So for this one, 1 squared minus 4, negative 3. And then when it's 0, negative 4. The nice thing here is I'm never going to have to go back in and sub back in for u, because these are in terms of u now. So I can just say, oh, well, what's the antiderivative of u to the negative 1? Natural log of u, the absolute value of u, right? I don't need a plus c here because I'm going to plug in like this. Crazy.
Wait, you don't plug it in.
Why don't I put a plus c? We're not done. You didn't do what? Right. You only use the plus c when it's an indefinite integral. For definite integrals, remember, that's fundamental theorem. Right. But if I have the bounds, I know the exact values. So now it's just 1/2 the log of 3 minus the log of 4. And just stop there. You don't have to plug in u. Well, so at some point in the problem, you have to plug in u. You just choose when you want to plug it in. You're either going to plug it in for the bounds, or you're going to plug it in when you find the antiderivative. So if I had not changed the bounds, and I said, okay, well, the antiderivative of this is log u, and I'm evaluating from 0 to 1, I would have to plug that. It would be the log of x squared minus 4 evaluated from 0 to 1. And then I'd have, you see the difference? At some point, you've got to give them in terms of the same variable. I find it easier to change the bounds. I'd rather change the bounds because whenever I find the antiderivative with the u, it's generally a lot easier formula than if I plug back in. Does that make sense? That's the only new stuff to it. What's what? When you take the integral there, it's gone. Go ahead. Yes. Yes. So here you would put a 1 in, log of 1 squared minus 4. You're still doing the same thing you did before, minus the log of 0 squared minus 4. In my opinion, it's easier to come over and convert, but whichever you prefer. Whichever makes more sense to you is the one you should do. All right, let's do another example. See if you can get this one. This one will be from your homework. No, because we're going to do definite integrals tonight. Let's do, y'all want to do a trig function or nah? We'll not do one first, then we'll do a trig function. All right, this is 59 from your homework. Mm-hmm. Evaluate the definite integral. You sure? Yep. Right. Always think you're looking for which one, if you take the derivative of something, which one has that derivative in there, and that would be your du. Your du would be your derivative part. But yes, always look for that highest power too. It's hard to get out of the mindset too of not looking at these operations that are over whole polynomials. This one was actually pretty nice as far as how it broke down here. What? Uh-oh. 2/3 times 3 to the 1/2. Is that what you said? 3/2. I mean, you can leave it like that. Is that what everybody got? No? Okay, let's do it. Let's do it.
So does that mean you have to do 1/5 minus 2? Because you're canceling it out?
No. So, because this is exactly the same as my du. So I've already said du equals blah. Well, if blah is in there, then I can just take the blah out and put the du in the place of it.
So you're taking that in the original problem.
Right. The reason we couldn't do that earlier is because if you go back and look at this one, I didn't have the entire du in there. Du was 2x dx, but I had x dx. So I had to make it look like that. To make it look like that, I had to give it a 2. But you can't just throw a 2 in there all willy-nilly because you got to keep it the same. That make sense? Yes, Miss McGee. Okay, so this is, you don't know, is it the trig functions? The inverse trig functions? I got you. I always come, and it looks really elementary. I always think people come look at whenever I do it. But if I need a 2 here, I still put a 2 here, and I still come over here and put the 1, because I visually need to see that, and I need to see it happen. That helps me. And so if you need to do that, don't feel bad. Lizzie's a little more conceptual in how she thinks about solving this. That doesn't make as much sense to me as doing it this way. But whichever, I mean, it's not wrong. All right, so from 0 to 1, if you mess up, it's going to be because you don't change your bounds. I'm telling you, that's where everybody always messes up. So make sure. And I got u to the 1/2 du. So what everybody got? Square root of u. Square root of u here. du. I'm going to go ahead and change my bounds. So when it's 1, u of 1 is going to be 1 to the 5th plus 2 times 1, which is 3. And u to the 0 is going to be 0 to the 5th plus 2 times 0, which is 0. Does that make sense? Remember your properties too. Sometimes when you change these bounds, it might be that the smaller number is not on the bottom. You can flip it and throw a negative out front, or you can evaluate it just the way it sits. It'll just come out kind of a little different for you. All right. What's the antiderivative of u to the 1/2? Yes. 2/3 u to the 3/2, evaluated from 0 to 3. Not once you take the integral, the du is gone. Yes. It happens when you take the derivative. Now you can plug in u, yes. So it's just 2/3 times 3 to the 3/2 minus, of course, the 0. And so this is where y'all were asking, can you leave it like that? I absolutely would. Well, if you plug in 0 for u, 0 to the anything power 0 times 2/3 is still 0. Good. I told y'all this what we do, even though it's a little bit new, it's still more practice with u substitution. Okay, it's the problems that are being given to you is why. It's the same thing. This one, yes. I will tell you, we practice with the trig functions and the inverse trig functions, but I don't sweat them quite as much because in the grand scheme of things, you might have 1 or 2 multiple choice questions on them. I've never seen them on an FRQ. I'm not saying they couldn't be, because they could, but the basic ones, yeah, but whenever you get into those inverse ones and stuff, those are not very heavily tested. So which one? The 1/1 plus x squared? It shows up a lot. What? I would definitely leave it like that, because otherwise you might make an algebraic mistake, because you can't multiply these two before you do the exponent, and you'd end up, ugh. So I'd leave it just like that. I think you do, but do you know the square root of 3? Yeah, me either. 2/3 square root of 3 squared. It's already simplified. Yeah, I know. That's why I said stop. Definitely stop. And at the end of the day, if you're multiple choice, that's the way they're going to have the answer. It's going to be either like this or like this. That's a 3 number. All right, one more. What time is it? Yeah, we got time. All right, I'm going to do one more, and then I'm going to let you work on your test corrections. If you're done with your test corrections, you can start your homework. Let's do cotangent is cosine over sine. Let's do this one. This is 64. What? Can't never could, Dylan. And you can. Evaluate. Yeah, is this what? Is it u substitution? I don't know. Is it? Do you know the antiderivative of cotangent? I don't. That's the, you're going derivative. Okay, so that might, I would have never known that. I wouldn't have, I'm not going to lie. Which one has a derivative of cotangent x? None of them, do they?
None of them have an integral.
Don't say what. That's exactly what I would do. If you have any tangent function, why would you not just write it in terms of sine and cosine, because they are derivatives of each other? Yeah, that's why I said in the beginning, wait, cotangent is... All right, so if I rewrite this in terms of sine and cosine, I got cosine over sine. Now, ooh, not Sid. Which one should you let be u? One. That's right. Could you do this if you let u be cosine x? Yes, you could. Yeah. You too, Coach Kersey. Thank you. There you go. Yeah. All right. So yes, you could. You could do. What'd you say? Right. You just have to do negative. Cosine x. Okay, that was. There's du. I get u negative 1 du. It's another natural log problem. Make sure you change your bounds. That's right. So u of 3 pi over 4, nice that these are just sine and cosine problems, right? The sine of 3 pi over 4, it's over 4. That should be easy for you. Just got to know what quadrant you're in.
Nothing is easy. Wait, can you just leave like that? After the actual value?
No, I was waiting on y'all to tell me the actual value. Right. As long as you're in the first or the second quadrant, you're positive there. And then u of pi over 4 is the same thing because I'm up top on my unit circle. Sorry, thank you. Sorry, thanks. And look, I don't even have to evaluate anything at this point because why don't I? That's one of those properties. 0.
Oh, word, is it a dictator?
No, but say it was
Yes, yes. And so the natural log of square root 2 over 2 minus the natural log of square root 2 over 2 is 0. Bruh.